Hello everyone, this is Rahim. I hope you're doing well and enjoying life. Welcome back. I'm here again with another video about 5G. And in this video, I'll explain 5G new radio synchronization process, frequency domain and time domain of synchronization signal block SSB, SSB burst and SSB periodicity, 5G synchronization signal block patterns, and finally I'll give you two examples: SSB beam sweeping in midband and SSB beam sweeping in high band. In 5G new radio, the initial access procedure is crucial for user equipment to connect to the network. One of the key steps in this process is getting time and frequency synchronization in the downlink direction, as well as physical cell identity through the Synchronization Signal Block SSB. The SSB consists of two signals and one physical channel. PSS, primary synchronization signal; SSS, secondary synchronization signal; and PBCH, physical broadcast channel. SSB refers to synchronization signal and physical broadcast channel block. For simplicity, I'll use synchronization signal block in this video. Here, I'll try to explain what exactly a 5G device can achieve by detecting the PSS and the SSS, as well as decoding the PBCH payload. By detecting the PSS, the OFDM symbol timing can be determined by the 5G device. The detection of the PSS enables the 5G device to estimate and correct frequency errors. To determine the physical cell identity, PCI, two identities are required: NID2, which identifies physical cell identity within the group, and NID1, which identifies physical cell identity group. Upon detecting the PSS, NID2 value can be determined by the 5G device. Upon detecting the SSS, the type of cyclic prefix CP can be identified. It can be normal CP, NCP, or extended CP, ECP. In fact, the CP type detection, NCP or ECP, can assist the 5G device to determine the slot structure. As you know, with NCP, we've got 14 OFDM symbols per slot, and in case of ECP, we've got 12 OFDM symbols per slot. Understanding whether NCP or ECP is in use is essential for a 5G device to correctly decode the radio frame timing within a 5G network. Detecting the SSS can help the 5G device to determine NID1 value, which is actually the physical cell identity group. A 5G device can complete frequency synchronization by detecting the SSS. Together, the PSS and SSS detections allow a 5G device to determine the complete PCI, which is essential for cell identification and synchronization in the 5G network. The PCI is crucial for a 5G device. It plays a key role in decoding the physical broadcast channel PBCH payload. Here is the PCI formula. There are 336 groups and 3 cell identities within each group. Totally, there are 1008 unique physical cell identities. The physical broadcast channel PBCH transmits both the master information block MIB from the layer 3 and some extra information generated at the physical layer. The MIB provides the essential system information that a 5G device needs to access the 5G new radio cell. A 5G device decodes the PBCH immediately after detecting the synchronization signal. The PSS and the SSS. Here, I'll try to explain what exactly a 5G device can achieve by detecting the PBCH payload and its associated demodulation reference signal DMRS. First, I focus on the MIB decoding. Upon detection of the MIB, the UE can obtain system frame number, which is actually 10 bits ranging from 0 to 1023, and its 6 most significant bits, MSBs, are embedded within the MIB. Subcarrier spacing. This parameter within the MIB is essential for a 5G device for creating the common resource grid. SSB subcarrier offset parameter is crucial for the 5G device to locate the SSB within the frequency domain. This parameter, represented by 4 least significant bits, LSBs, defines the frequency offset of the Synchronization Signal Block, SSB, with respect to the overall channel bandwidth. This frequency offset is known as KSSB. In case of frequency range 2, FR2, KSSB ranges from 0 to 11, and the 4 LSBs are sufficient to represent this range. However, in frequency range 1, FR1, KSSB ranges from 0 to 23, and 5th bit is required. This 5th bit, the most significant bit, MSB, is also determined at the physical layer. DMRS type A position. This parameter is essential for a 5G device as it indicates where to find the demodulation reference signal in the downlink transmission, which is necessary for demodulating the physical shared channel PDSCH mapping type A. PDCH config SIB1 includes 8 bits. This parameter essentially guides the 5G device on where and how to look for System Information Block Type 1, SIB1, which contains critical information for network access and operation. Cell barred. This parameter refers to a flag that indicates whether a cell is barred or not. If a cell is barred, the 5G device is not permitted to select that cell. This means the 5G device should ignore the cell and search another cell to connect. Intra-FREC reselection. This parameter controls whether a 5G device is allowed to reselect to another cell operating on the same frequency when the highest ranked cell is barred. The physical layer of the base station attaches additional information, 8 bits, to the MIB before it is processed for transmission across the air interface. As you know, the demodulation reference signal DMRS is transmitted along with PBCH to assist the 5 device for demodulating the PBCH payload. The PBCH DMRS contains information related to SSB index. Here you can see the essential information that a 5G device can get by combining the information obtained from PBCH DMRS with the additional data added to the MIB at the physical layer. SSB index: when 5G new radio cell performs beam sweeping technique to send multiple SSBs, you can identify each SSB beam with SSB index. Half frame index, which can be first half frame or second half frame. SSB subcarrier offset 1 bit, most significant bit MSB, which is required for frequency range 1, as I mentioned in MIB decoding. And system frame number 4 LSBs. As I mentioned earlier, getting the synchronization signal and decoding the MIB content guides the 5 device to read the system information block type 1, SIB1. In this video, I'm not going to present the information included in the SIB1, but one of the key information included in the SIB1 is offset to point A, which is crucial for the 5 device to understand the common resource block number where the SSB is located in the 5G new radio channel. Here, I'll try to show you a diagram for more clarification. The common resource grid is created based on the subcarrier spacing extracted from the MIB and the transmission bandwidth of the channel, which is obtained from SIB1. Point A is a common reference point identifying the center frequency of subcarrier 0 of common resource block 0, CRB 0. A 5G device, by combining the offset to point A and KSSB, can deduce the exact location of the SSB within the entire channel bandwidth. From a bandwidth perspective, the SSB consists of 12 resource blocks for a 3 MHz channel bandwidth as specified in 3GPP release 18, or 20 resource blocks for other channel bandwidths. The SSB can be configured at any point within a carrier's frequency range that is aligned with the subcarriers of the common resource grid, offering more flexibility than the fixed center frequency configuration of LTE. The SSB bandwidth can range from 2.16 MHz to 230.4 MHz. In the time domain, the Synchronization Signal Block SSB consists of 4 consecutive OFDM symbols. In the frequency domain, as I mentioned earlier, the SSB consists of 20 resource blocks, 240 subcarriers. For the channel bandwidth of 3 MHz specified in release 18, the SSB occupies 12 resource blocks in the frequency domain. The 5G new radio cell transmits the PSS on the first symbol, the SSS on the third symbol, and the PBCH on the second, third, and fourth symbol. In 5G new radio, with the help of beam forming and beam sweeping, there is a possibility to transmit synchronization signal blocks in different beams in a time multiplexed manner. The set of SSBs within a beam sweep is referred to as an SSB burst. An SSB burst includes one or more SSBs and is confined within a 5 milliseconds time window, which is actually half of a radio frame. Each SSB belonging to an SSB burst is allocated to a beam. The maximum number of SSBs within a burst depends on the operating band. The GMB informs the 5G device the periodicity of half frames, SSB periodicity for reception of SSBs for the serving cell. The SSB periodicity can range from 5 milliseconds to 160 milliseconds, depending on the network configuration. During an initial cell search, the SSB is repeated at least once every 20 milliseconds. In 5G New Radio, the configuration of SSB bursts is influenced by several factors or parameters, including the frequency range, frequency range 1 or frequency range 2, operating band, subcarrier spacing, and the starting OFDM symbols of the SSB within the burst. The 3GPP has defined 7 distinct patterns A to G to support the diverse configurations of SSB burst parameters, catering to different deployment scenarios and spectrum utilization strategies. Here, I'll try to depict the SSB patterns based on the frequency range and subcarrier spacing. SSB pattern A is used in frequency range 1 FR1 with a subcarrier spacing of 15 kHz. In case of below 3 GHz, a maximum of 4 synchronization signal blocks are transmitted within a burst, and for the frequency range between 3 GHz and 7 GHz, a maximum of 8 synchronization signal blocks are transmitted within a burst. For this purpose, we have two cases for SSB pattern A, case A1 and case A2. Let's look at the position of synchronization signal blocks within a burst. As you know, an SSB burst is always confined within a 5 milliseconds time window, which is actually half of a radio frame. Therefore, the synchronization signal blocks can be transmitted within the first half frame or the second half frame. For simplicity, we consider the first half frame. For the SCS of 15 kHz, slot and subframe duration is 1 millisecond. Therefore, there are 5 slots within half of radio frame. For case A1, 4 synchronization signal blocks are indeed transmitted in slots 0 and 1. 2 synchronization signal blocks per slot. For case A2, 8 synchronization signal blocks are indeed transmitted within slots 0, 1, 2, and 3. Here, you can also see the position of the 2 synchronization signal blocks within slot 0. SSB pattern B and C are used in frequency range 1 FR1 with a subcarrier spacing of 30 kHz. Same as SSB pattern A, there are 2 cases for both patterns and a maximum of 8 synchronization signal blocks are transmitted within a burst. Only the position of the synchronization signal blocks within a burst are different. First, let's look at SSB pattern B. As you know, slot duration for SCS of 30 kHz is 0.5 millisecond. Therefore, there are 2 slots per subframe. For case B1, 4 synchronization signal blocks are actually transmitted in slots 0 and 1. And for case B2, 8 synchronization signal blocks are actually transmitted in slot 0, 1, 2, and 3. It only takes 2 milliseconds to transmit 8 synchronization signal blocks. Here, you can also look at the position of the 4 synchronization signal blocks in slot 0 and 1. Here we can see the SSB pattern C. As I mentioned earlier, only the position of the synchronization signal blocks within the burst is different. For the frequency range 2, 3GPP has specified 4 SSB patterns. I mean pattern D, E, F, and G. In this slide, we'll look at pattern D and E, and in the next slide, we'll see pattern F and G. SSB pattern D is applicable for SCS of 120 kHz, and a maximum of 64 synchronization signal blocks are transmitted within a burst. As you know, the slot duration of SCS of 120 kHz is 125 microseconds. Therefore, we have 8 slots within a subframe, which is indeed 1 millisecond. Here, you can see 64 synchronization signal block within a 5 milliseconds time window, which is actually half of a radio frame. Therefore, in SSB pattern D, it takes approximately 5 milliseconds to transmit 64 SSBs. For the first 16 SSBs, you can also see the position of SSBs in slot 0 to 7. Here, you can see the starting OFDM symbol of SSB 0 to 7, which are located in slot 0 to 3. SSB pattern E is applicable for SCS of 240 kHz, and same as SSB pattern D, a maximum of 64 SSBs are transmitted within a burst. The slot duration is 62.5 microseconds. Therefore, we have 16 slots within a subframe. Here, we can see the SSB's position within SSB burst of pattern E. As you can see in the diagram, it takes less than 2.5 milliseconds to transmit 64 SSBs within a burst. 3GPP introduced the subcarrier spacings of 480 kHz and 960 kHz in release 17. In release 18, 3GPP expanded on the use cases related to these 2 new subcarrier spacings. For this purpose, 3GPP specified SSB patterns F and G in release 17. Both SSB patterns, I mean pattern F and G, support the transmission of maximum of 64 synchronization signal blocks. In the case of pattern F, which uses a subcarrier spacing of 480 kHz, the slot duration is 31.25 microseconds, resulting in 32 slots within a subframe. For pattern G, with an SES of 960 kHz, the slot duration is 15.625 microseconds, leading to 64 slots within a subframe. Here, we'll see the position of 64 SSBs in pattern F and pattern G. As you can see in the diagrams, it's obvious that it takes approximately 1 millisecond to transmit 64 SSBs within a burst in SSB pattern F, and this duration is less than 0.5 millisecond in SSB pattern G. Here, I'll try to show you three tables related to frequency range 1, FR1, and frequency range 2, FR2, which includes essential parameters for each operating band, assisting the 5G devices in receiving synchronization signals. Subcarrier spacing, SSB pattern, and synchronization signal raster. In case of subcarrier spacing, 3GPP has specified a set of 6 subcarrier spacings: 15, 30, 120, 480, and 960 kHz. The SCS values of 15 kHz and 30 kHz are applicable in frequency range 1, FR1. The SCS values of 120 to 140 kHz are applicable in frequency range 2-1, and the SCS of 120, 480, and 960 kHz apply to FR2-2. The default subcarrier spacing has been specified for each operating band. For some operating bands, 3GPP has specified 2 default subcarrier spacing. For instance, NR operating band N41 supports 15 and 30 kHz as a default subcarrier spacing. 3GPP specified in release 17 a new NR band as a FR2-2, I mean N263, which is an unlicensed band. This NR operating band supports the SCS of 120, 480, and 960 kHz. I should point out that the SCS of 960 kHz is not used for initial access. In case of SSB pattern, as I mentioned earlier, 3GPP specified 7 patterns, I mean A to G. Case A and B and C in FR1, case D and E in FR2-1, and case D, F, and G in FR2-2. Global Synchronization Channel Number GSCN is actually a set of numbers that identifies frequency position of Synchronization Signal Block SSB on Synchronization Raster. Here, I'll try to show you how a 5G new radio cell performs SSB beam sweeping with digital beamforming in the midband utilizing SSB pattern C. For simplicity, I'll consider the SSB burst is located within the first half frame with the SSB periodicity of 20 milliseconds. I'll show you an animated presentation without speaking. In this slide, same as previous slide, I'll try to present to you SSB beam sweeping with analog beamforming in the high band utilizing SSB pattern D. Similar to the previous slide, I'll present this one without speaking. Thank you for being with me in this video. Please feel free to ask any questions. I'm here to assist you in understanding this topic. You may leave your comments or questions under this post. For more information related to the 5G system, you can refer to my page in LinkedIn. Finally, if you require any courses related to the 5G system, including 5G Core and 5G RAN, or if you are interested in potential collaborations, please send inquiries through LinkedIn.